Morning, everyone. So yesterday we introduced our main concept on equilibrium. So let's just highlight some key features here. In chemistry here, remember we refer to our equilibria as dynamic equilibria. Dynamic sort of implies things are still continuing. In this case here, we can make a note to ourselves here. Microscopically, that's the particles themselves as they collide here, microscopic reactions continue to occur. So they still occur where reactants are forming products as products are forming reactants. And yet macroscopically, outwardly, it looks like nothing's changing. So macroscopic properties, macroscopic characteristics remain constant in time. Macroscopic properties are constant. What are some examples of macroscopic properties? It could be color intensity. It could be the amount of material. So if I have a saturated solution, it looks like the amount of powder is just sitting there. It looks like it's not changing. That would be a macroscopic property. Pretty much outwardly, it looks like nothing's changing. How could it be that both of these things are true? Things are changing and yet they're not. In this case here, our sort of conclusion here is as reactants become products, the products are actually forming reactants at exactly the same rates. So we can use this conclusion here. The forward rate equals reverse rate. Thinking about that hockey game analogy here, as long as three players go off and three players come on at exactly the same speeds, it doesn't have to be the same players on the ice, although I'm going to always have 5 skaters on my team. So forward rate is equal to reverse rate. A couple other features that we talked about here. The concentrations are constant. That sort of implies that they're the same, but the only thing they're the same is they're constant in time. They're no longer changing in time. However, again, I'm going to emphasize here, in general, the reactants are not equal to products. So we can have a hockey game that has 5 skaters on the ice and 20 players on the bench. The 5 doesn't have to equal the 20. Today we're going to introduce our main concept, which deals with a little bit of the math that we're going to see. And that's going to be called this one here, the equilibrium expression or the equilibrium constant. So for the equilibrium constant here, technically you can just call it K. It's just a letter that represents this constant here. Depending on the type of equilibrium that we have, we're going to mainly do Kc, which basically is, it's the equilibrium constant. It's this number that describes equilibrium where we express everything in concentrations. Later on in other textbooks, you may see Kp, where I have things in partial pressures. We're going to see KSP, for a little bit of solubility towards the end of this chapter here. In our acid-base chapter, we're going to have a lot of Ka, Kb, Kw. Pretty much the K itself just tells you equilibrium constant. It's this thing that I'm going to be introducing to you. It's a number that describes equilibrium, but depending on what equilibrium we're talking about, sometimes we end up changing the subscript here. And in Chem 12 here, they prefer to just generically say this as KEQ. So just look out for that notation here. So let's just make a connection to some of our kinetic stuff here as we introduce this equilibrium expression. Experimentally, chemists have discovered a mathematical relationship between the concentrations of products and equilibrium. So let's pretend we have the elementary process. The lowercase here would be the coefficients, A and A, B and B, C and C, D and D. So just for simplicity here, we're going to assume first order. Assume first order in all species. So that, remember, that has to be experimentally defined here. The coefficients themselves don't necessarily have to be 1, but just in terms of the rate, it is just first order. We're going to, let's say we start off with all reactants, they just steadily become products. We are such a reaction which actually hits equilibrium, so the C and C will end up colliding with good energy, good geometry. They're going to end up having the reverse reaction. So there's my equilibrium arrow. Just a small note here, careful when we do the equilibrium arrow, it is sort of this reversible sort of symbol. Earlier in grade 11, we did this sort of double-headed arrow. That double-headed arrow meant resonance, so we want to reserve different arrows for different features. So in this case here, if I actually, since equilibrium is interested in looking at the rates, let's do our sort of kinetic stuff here and see if we can identify the rates. So the forward rate is going to be K, forward. The forward rate involves the reactants. A has to collide with B. It's going to depend on A. Again, we're going to just do order 1 for simplicity here. B, order 1. So that's the forward rate here. The reverse rate, very similarly here, the reverse rate involves taking your products. We're going to have some other rate constant because that's going in the opposite direction, but it's going to only depend on the C and D colliding. So C, let's say also first order, D also first order. And now for equilibrium, because we've waited long enough for the concentration to stay constant in time, we're basically saying the forward rate actually has to equal to the reverse rate. So if I just sort of sum that up a little bit here, what we're going to do, I'm going to bring all these rate constants over to the left-hand side. So I'm going to say Kf. I'm going to divide over the K, I don't know why I said P, K of R, reverse reaction. So it's basically, it's this guy is equal to this guy, right? So I'm going to divide the K reverse over here, and I'm going to divide the A and B over to the opposite side here, and we're going to end up with here C times D all to the power 1 divided by A times B. And this is going to be referred to as our equilibrium constant expression. This is, again, in grade 12, we would just call this generically, it's the constant for equilibrium. For IB, we prefer to just say Kc. It's the equilibrium constant for the concentrations. Let's make a note here. Since Kf and Kr are constant for a given temperature, the KEQ is a constant as long as the temperature doesn't change. So we're going to basically, both of these themselves would have been numbers. Remember, we're thinking Arrhenius. We have K is equal to AE negative EA over RT, like that. So the K's themselves don't have to equal each other, but as long as I'm at the same temperature here, it's the same activation barrier, although I'm going in sort of different directions. Both of these are going to be constant at the same temperature. When I divide it, it just becomes another constant, and now I can just say, therefore, the KEQ, which I'm actually going to call KC. So let's just rename this one. So KC, I know it has something to do with the rate constant in the back. I know that's why it's only temperature dependent, but it's basically going to be the concentration of C. In case, sure, we could still be in first order here, but in case we actually had coefficients here, we're actually going to go C to the power C, D to the power D, all over A to the power A, and B to the power B. So that's just a sort of rough definition for you here. This time I want you to note where the A, B, C, D are the stoichiometric coefficients. Remember, in the last chapter, we were making this big deal, and we were saying, oh, you can't just look at the coefficients and just predict what the order of reaction is. That still is true. But in this case here, basically, it will be the coefficients that actually enter our KEQ expression, our KC expression. So these are the stoichiometric coefficients. More for simplicity here, you can just say the KEQ or KC is generally a number that describes how many products we have, the ratio with the number of reactants. While I have it here, products over reactants here, what does it mean if this KC is very large? So let's just do it on the side here. If your KEQ or KC, if this KC is bigger than 1, for this fraction to be bigger than 1, that means I have way more products than reactants. As I've written, we can say the concentration of products is way bigger than the concentration of reactants. Numerator is bigger than denominator. Because this number here is relative to concentrations, concentration can't drop into the negatives. The Kc can't actually become negative. But if I say sort of Kc as less than 1, it sort of implies here it has to be sort of bounded by 0 and 1, can't drop into the negatives. We can say the reverse, products are less than reactants. That's the only way for the fraction to actually be less than 1. So just getting you familiar with different ways of saying this. More reactants, or you can even say this terminology here, reactants are favored. Reactants are favored. That means we have an equilibrium system. Yes, we've hit this balance. Yes, the forward rate is equal to reverse rate, but we are at such a temperature that we actually have more of the A and B, more of the left-hand side than the right-hand side. What if the Kc is roughly 1? So what is KEQ here? What if it's about 1? Well, for this fraction to be about 1, pretty much we have, well, our products would have to be roughly the same as reactants. The reason why I'm not saying equal is because sometimes when you have different powers here, the numbers themselves don't have to equal each other. Right? So that's what this equilibrium constant gives you here. The expression is just products over reactants using the numbers from the coefficients, and then the understanding the size of this equilibrium constant, this number, actually just tells you, while all of these are at equilibrium, when you've hit this balance, do you end up with more products, more reactants, or about the same as both? You won't see the equilibrium constant abbreviated as KEQ, so there's some other common notations. I've been saying in IB we prefer to say KC. Kc is this equilibrium constant. Pretty much we're dealing with solutions. Solutions we're talking about are sort of solids into liquids into sort of aqueous here. So if we imply everything in concentrations, we can use Kc. If I have all gases here, we can refer to something called partial pressure. We'll see a little bit of it in a later lesson here. Let's say the KEQ used for gases. If we have everything expressed in partial pressures, it's still going to be a general ratio between how many products with how many reactants. But again, it's just a slightly different lettering. Just to give you a feel of what this partial pressure is, again, we'll do a small lesson on this later on. But basically, we're going to have a liquid. At first, the liquid is just going to gradually evaporate. Basically, you might have the lucky particles here. Remember, in a given system, maybe on average, they don't have enough energy to actually boil off, but you might have the really fast-moving particle that can actually escape the system. We would have to be in a closed system to make sure the gas doesn't escape. So once the gas particles are sort of built up to a certain amount here, the gas particles here can then sort of push downwards on the surface again. When we're in equilibrium, we refer to that as the vapor pressure of that particular gas. So if I have sort of the vapor pressure of the products divided by the vapor pressure of reactants, that also expresses this ratio that we're interested in. A substance can only be included in KEQ if it possesses a concentration. Now that's a fairly strange statement here, because concentration here, moles over volume, if we're talking dissolved material, whether it's dissolved solids and liquids or gases and liquids here, that makes sense, because that's actually telling you, well, it's how much powder or how much gas do I dissolve in my swimming pool. What we're going to see is we're going to ignore two things that don't actually have concentration per se. One that we're going to always ignore is we're going to ignore all solids. Doesn't matter which side of the equation that it ends up on. So ignore all solids, because solids they always like saying this one here, they have a constant composition. I think of it as they have a constant density, and that's why we ignore them. So for example, if I have just a solid, we know the particles don't have much energy, they're just sitting around vibrating in place here. If I said, what is the concentration of the solid? You would say, well, what's the material that makes up these powders divided by the volume that the solid itself makes up, rather than the volume of the pool that it ends up dissolving in. So great, that gives you some concentration, that does give you some number. Notice here, I could actually look at 2 blocks. When I have 2 blocks, now I have twice the number of particles, right? Shouldn't concentration change? But if you have more particles as well, you've also increased the amount of room that's sitting in. Let's just put some numbers to this here. Let's say I have 6 particles in 1 box of room. That sort of has like a concentration of 6. Now looking at both boxes together, you would say, oh, we have 12 particles, way more. But now it's taking up 2 particles of room. You notice that 6 there, roughly, is remaining constant. So I think for solids here, yes, you can have more solid. So let's make that analogy. You can have more solid, more or less solid. So the amount can actually change. But what we're referring to as the concentration, this density, this ratio here, but the concentration is the same. And in that case there, instead of really, when I go products or reactants and saying, oh, A is actually a solid, A is actually a number, because that number would never change, I'm basically going to absorb it into the KEQ, and basically you could just totally drop it. The concentration here never changes. For exactly the same reason here, we will also ignore what's referred to as pure liquids. And you will know that it's a pure liquid if it is the only liquid, only thing that's denoted L, in the entire equilibrium, left side or right side. In the very same way here, liquids also have constant composition. So you have, let's say this is just water. For water, we put liquid instead of aqueous because we don't think water dissolved in itself. Well, if I have a pure substance of water here, sure, I have a little bit more energy, right? I'm sort of slipping and sliding past each other here. The density or the concentration will be the particles divided by this volume. That still remains true. That's totally fine. But again, as you shift equilibrium, as you dissolve things or whatever, you can't change this concentration because that ratio, it's actually fixed. What if I actually have 2 liquids in solution? Liquids and liquids have something referred to as, I think they call it molar volume, not with gases this time, but basically sometimes when you mix, let's say I mix 10 milliliters and 20 milliliters, you totally expect the total volume to be 30 milliliters. If we have 2 pure substances mixed into each other, sometimes the total volume would actually be less than 30, where the particles of one liquid actually fill in the gaps left behind by the other liquid. So if I have more than one liquid, it is possible that this density or this concentration may change, right? So let's just make a quick example on the side here. Let's just deal with the equilibrium system. Let's go A as a solid plus 2B as a gas is in equilibrium with 3C as a liquid. If I ask you, can you write for me the equilibrium expression? So can you write for me this product over reactant ratio applied to this reaction? You start off, okay, we're going to call it Kc. Kc in general is supposed to be products over reactants. We just need to decide who is a product and who's a reactant. Again, by convention, our reactants are on the left side, products are on the right-hand side here. Our products are going to be C. In this case here, C is actually a liquid. So I'm going to show you sort of more detail than what I'm going to do here. So let's say C here, that should be cubed. And then we have our reactants, A, that's to the power 1. So I'm just going to do it to the power 1. If I have multiple reactants, they get multiplied together. B is a squared. But again, looking at this sort of note here, because solids and liquids have constant composition, this is the only L in the entire equation. This is a solid. Basically, the L number is not expected to change, and the solid is not expected to change. So mathematically, what we do is by the time we actually differentiate and we actually tell you what the C is, since that number doesn't change, let's just absorb it into Kc. Let's like divide the C cube over there, let's times A over there, and let's just get some new equilibrium constant. So therefore, my equilibrium expression, upon ignoring the C, ignoring the solid here, my Kc, it's a new Kc, right? It's different from the one from earlier. It had absorbed some of these constant numbers here. The new Kc, what I'm going to say is still 1 over B squared. Now, you see that in that case there, I did ignore it, but B is still a reactant, so that still has to come in the denominator. So it does depend on sort of which way I write this equilibrium, right? So just introducing, this is what's referred to as equilibrium expression. This Kc here is called an equilibrium constant. And the C, again, just implies we are just using concentrations to express this ratio, equilibrium constant. Right. We're going to get into this next statement a little bit more in the next lesson, but I'm just going to quickly introduce it to you here. We have a principle referred to as Le Chatelier's principle. And basically, one of the applications to this, sort of a starting application, is if I have a beginning system that's not in equilibrium, the system will naturally head towards a situation of equilibrium. Everything will sort of work itself out to this sort of balanced state here. So what's going to happen here is, as such, we can predict, right, because any system, pure reactants, pure products, will naturally hit equilibrium, we can predict the direction equilibrium. We can predict the direction to approach equilibrium, and we're going to use the terminology of shifting in tomorrow's lesson. So just keep watch of that language here, shifting. I can shift left to go to equilibrium, make more reactants, or I can shift right. So let's see if we can do this here. If my KEQ is large, meaning I'm at a temperature where the ratio is supposed to have a lot of products over reactants, right? For my ratio here to be large, I want the whole fraction to be big. For the fraction to be big, I need the numerator big, the reactant small. We can say the equilibrium favors products. I have more products. Even though we've hit this balance, we're at a temperature where we have way more products. So that's going to be a situation where I have a ton more products. We've still hit equilibrium fine. The forward rate equals reverse rate. But we're at a temperature where we have a lot more concentration of products over reactants. Or vice versa here, if the KEQ is small, if the KEQ is less than 1, if this fraction here is tiny, right? Think products over reactants here. If this thing here is supposed to be tiny, products have to be low, reactants have to be high. Basically, we need to have way more reactants. Another way, I can just getting you familiar with the wording of it here, you can say the equilibrium, EQM, equilibrium lies towards products. And that's the direction we want to head towards. If I'm not in equilibrium right now, I need to then generate more reactants. Right? So on the back side here, just a little bit more. What's important for you to note here is the KEQ. Remember, we had done a rough derivation earlier. The KEQ is a rough comparison between the sort of forward constant and the reverse constant. These ones here are only temperature dependent, right? Through the depends on temperature. So through the Arrhenius equation, the rate constants themselves don't change as long as the temperature is the same. And therefore, even though the Kf doesn't necessarily have to equal Kr, if I have a constant divided by constant, this one here has to be the same number. So in this case here, KEQ does not change in the if you just come in and change concentration, change pressure, that's not a temperature change. The rate constant aren't expected to be any different. The KEQ does not change. Right? There is one case, this is important. When does KEQ actually change? The one case here is if you actually change temperature. So, change temperature. Because if you change temperature, the Arrhenius plot here would be a little bit different. The rate constants themselves would be a little different, so therefore the ratio itself would be different. So, case in point here. We're going to have our Haber process again. We like it because everything's gas, so there's nothing I need to ignore in this case here. Currently, it's written as an exothermic reaction. The KEQ is currently 0.050. I can already make a conclusion here. Because the KEQ is small, I know that the reactants are favored. Right? I should have much more reactants than products. Note, if we increase temperature, well, what's going to happen here is, let's imagine this entire thing is inside a container. I'm going to stick in a microwave. I'm going to heat up the entire box. One way of doing this here is, as I increase temperature, we're going to see this a lot more in tomorrow's lesson here, we can actually think of the heat chemical as a heat number as a chemical. If I suddenly increase temperature, it doesn't like that. And what's going to happen in tomorrow's lesson, we're going to see is it actually tries to shift away. It's going to get ammonia to absorb in some of that 92 to then reform reactants. So what's ending up happening here? I'll write it down for you. For increasing temperature, the equilibrium, EQM, the equilibrium will shift to the reactant side. So if you think about this KEQ here as a ratio, KC was supposed to be products over reactants. If we're going to talk about this as a stress in tomorrow's lesson here. If I stress out the system and I end up generating more reactants, the reactants goes up, the products goes down. My fraction, which would have been 0.050 at this temperature, now I'm at a hotter temperature. My fraction here has actually gone down. The KC has actually decreased. So in that situation here, KEQ will decrease. That's not something you need to memorize. You can just find that out here just from this derivation here. Let's go the opposite way. What if we decrease temperature? Again, this will make a little bit more sense in tomorrow's lesson once we talk about these shifts here. If I decrease the temperature, I basically look at it as I pull down this heat term. Equilibrium doesn't like that, and equilibrium is actually going to respond, and it's actually going to shift towards the right. So in this case here, equilibrium shifts towards products. It's going to end up making more products, and therefore if I have KC as products over reactants, if I have a situation where only products go up and reactants go down, my KC will actually go up, and therefore we can say here my KEQ increases. Right? We can actually do that a little bit more mathematically as well. So we can predict this shifting direction here. For the reaction above, let's say we increase N2 and I increase it to say double. So what I'm going to do here is I'm going to start off. Let's start off with the equilibrium expression. KEQ is supposed to be products over reactants. None of them are solids or liquids, so I include all of them. The KEQ is supposed to be ammonia squared divided by N2. Remember, for this equilibrium constant expression, we just basically use the coefficients for the powers. What we've done, we were at equilibrium, we were at this ratio 0.050 at 55 degrees. This time, I'm going to give it a slightly different name. I'm going to call it Q. Our Q here is actually just sometimes you refer to it as a trial KEQ, as a test KEQ. And basically what I've done is, from the situation where you were, right, we had the NH3 minding its own business, what I did is I suddenly did twice N2. So twice the concentration N2 was my change, and then I have my H2 cubed. Well, what would happen then is, suddenly, I went from a KEQ which is 0.050, and suddenly my Q is actually half what it should be. Because I didn't change temperature, I would imagine that the KEQ stays constant. So KEQ is constant since the temperature is not changed. And therefore, what's going to happen is the Q, right now here, the Q is a product over reactant. Right now, it's only half what it should be. The Q has to get bigger so that it actually approaches KEQ. So we can write that down here. Currently, by doubling the N2, that's all I did in my system here, the Q is less than KEQ. So if I think of Q as products or reactants, right now my number is too tiny. How can I get my fraction to be bigger? My fraction to be bigger implies I need to shift to the right. I need to make more products, and I need to drop in reactants. I don't have enough products for my ratio to be large enough. So in this case here, we can say the reaction shifts to the product side. I need to make more products. And let's see if we can flip that logic around here. What if the N2 is halved? Again, the KEQ is just minding its own business here, but now I just poke at the system. We're going to do all these pokes a little bit more in tomorrow's lesson as well. I'm going to take the NH3, right, that stays the same, and all I've done this time is I've taken half of what the N2 was. Because that one there is in the denominator, you can think of that 1 over half is actually 2 times this. So therefore, what if my Q is suddenly twice as big as it should be? In that case there, if my trial value is much larger than KEQ, my product over reactant ratio is currently too large, I need to shrink this ratio. So products over reactants has to shrink. For this to shrink, I need to lose my numerator and increase my reactants. For a reaction that's reactants and products like this, I need to make sure to lose products, I need to shift to the left. So therefore, the reaction shifts left towards reactants. By suddenly changing the N2, I didn't have a lot of N2, it basically shifts to replenish some of the N2 there. Note this numerical arguments here agree with our reaction kinetics. So our chapter 6, because the whole notion there is, well, because KEQ only depends on the rate constants, sure, if I change temperature, the number itself will change. In this second situation, because I'm only changing concentration, temperature is actually constant. The Arrhenius equations will be constant, and therefore the equilibrium constants will actually be the same as well. Right? So in general here, whenever Q, our test KEQ, is larger than KEQ, right, my ratio here is too large, so I need to shrink this ratio. We can make a conclusion that the equilibrium shifts left. In contrast, when Q is less than KEQ, when you do something, in tomorrow's lesson, we're going to change temperature, change pressure. We're going to poke at the system somehow. My ratio currently is too tiny. I need to get my fraction to be larger. To get it larger, I actually need to gain products. So in this case here, we can say the equilibrium shifts right. For temperature, it's a little bit harder to conclude because it's going to depend whether we're X or endo. So in this situation here, let's pretend we have an exothermic reaction as written. For an exothermic reaction, the heat term is on the right-hand side. We had saw when I increase the temperature, it shifts towards the reactants. So for exothermic and exothermic only, increase temperature shifts left. And what we did is we decrease temperature here. When we decrease temperature, it shifts right. We're going to verify what about the endothermic reaction in the opposite case here. Endothermic means the heat term is on the opposite side, and it's sort of in the same view here. If you increase temperature, this one here will actually shifts right. And if you decrease temperature, it actually shifts left. Right? So there's a couple questions for you to just practice here. Don't worry, we'll get a lot into this shifting in more detail, the Chateli's principle in tomorrow's lesson anyways. They just wanted to introduce to you what is this equilibrium constant, what is this equilibrium expression, and basically the size of this number tells you, although we are at equilibrium, although we are at this balance, we actually have a situation where forward rate equals reverse rate. So if you can just try some of these questions here, they give you a bunch of these equations here. Remember, anytime there's a solid, you're going to ignore it. If it's the only L in the equation, you're going to ignore it. So just make a note there. This part here does refer to the N2 NH3 concentration here. At 55 degrees, you can use this number here. At 55 degrees, the KEQ is 0.050. You can use that to answer a couple more questions. So one other conclusion I just want to leave you with here before we do tomorrow's lesson here. Only temperature changes KEQ or KC, right? Because KC, remember at the heart of it, KC depends on the rate constants, K forward divided by K reverse. Now there is a couple little manipulations I can do that sort of, it seems like it counteracts that. That is a conclusion that we're going to take away. But let's just analyze a couple more situations here. What if we have, let's say, A is in equilibrium with B, and that has a KC, right? So KC is supposed to be products over reactants. It's just B divided by A. Fine. what if I took this equation, I'm sort of cheating here. What if I wrote the equation backwards? What if I did B first and then A, right? Does that change Kc? Well, sure. Kc is supposed to be products for reactants. This time A is actually a product and B is actually a reactant. So therefore, what happened here is when I reversed the reaction, so going from here to here, when I reversed the reaction, what ends up happening is the Kc is actually taking the reciprocal. Now that's sort of a little bit of a cheat because normally we're given just one equation, we're just studying it exactly as written, but sometimes in multiple choice they just say, okay, well, if I actually change the equation on you, how might the Kc respond? What else can I do to the system here? What if I doubled everything? What if I took the A and B, and what if I made it, let's say 2A becomes 2B? Does that change the equilibrium? Well, then we can write out the expression again. Kc is equal to B squared over A squared. Compared to the initial here, you see that when I actually doubled the equation, or scaled it in any which way, we ends up, in this case here, we ended up taking the square. Again, you don't even memorize this. You just do a product over reactant based on the equation that they give you, and you just compare it to what we did earlier. So if you times 3, it's going to have to the cube. What if I half the equation? So it's still going to be a power, but let's see if we can do this here. What if I had half A equilibrium with half B? The Kc would then be B to the power of half divided by A to the power of half. If you remember from your math classes here, if you take half, the power of half, this one here actually just means you just take the root. So in some sense, it doesn't change the fact only temperature is going to change Keq. That's going to be really important for us through the rest of the chapter. But if they change the equation on you, we can study this here. I'm going to let you verify this one here. What if I end up adding two reactions together? So what if I had, let's say, A and B become AB, and then A, B, and C become A, C, and B. Right? So sort of like a reaction mechanism. Now, to be sure, both of these have their own expression. I'm going to call it Kc for the first reaction is AB divided by A and B. For the second reaction here, the Kc is AC times B divided by AB and C. What if I added these two equations together? So the operation is add the equations. So if you add it, any things that cancel, they cancel. So in this case here, we're left with A and C should become AC. You should be able to find for me the total, the new Kc that I get, Kc prime, it's actually going to be multiplied by Kc double prime. So you can do that math there. AB divided by A and B. Multiply it by the AC. We're going to do a lot of this work here in our acid-base chapter coming up. But basically, you're just matching it up there. And in this case, you see, oh, great. The AB cancels the AB. B cancels the B. And therefore, I get AC as a product. Perfect. Matched up with A and C as a reactant. All right? So just have a look at some of these questions here. Try out writing some equilibrium expressions for yourself. We'll deal with all this shifting stuff here. Basically, how the equilibrium responds in tomorrow's lesson. Thanks, guys.